mention this interesting business. This is by way of a little break, little diversion. That usually we think that if you take an object and you rotate it by 360 degrees, by 2 pi, it returns to its original state, right? So we kind of tend to think that 2 pi rotation is the identity, puts things back to where they started. But that isn't quite the case, interestingly. It turns out that 4 pi can be better than 2 pi. And I remember reading about this and I just didn't want to believe it. But it's true, and Feynman talks about this.
Feynman. Richard Feynman?
Richard Feynman. And he makes the parallel with there are dancers in Bali, which beautiful girls, who hold a candle in the hand. And so they have a candle and a saucer, I think, in their hand. And they do, so now I'm going to rotate this thing by 180 degrees. And so you can see that I'm not back to where I was. But if I keep rotating in the same way, then you get back to where you were. Right? So, of course, I'm not beautiful. But I didn't want to believe that this was true. And so then I did an experiment. And I want to show you guys because it really is amazing. So this is too complicated. So the idea is this. You take a book or any kind of an object. I just took a piece of plexiglass here. And you take a rubber band and you, simplifying the experiment, and you take a rubber band and you, so this is just an ordinary flat object, and there are these nice flat rubber bands, and you tie them, you take a rubber band and you glue the end of the rubber band to a wall over there, and this one over there, and one here, and one here. And now if you rotate this thing 360 degrees, you got a hell of a mess, right? Everything is twisted up and it's crazy. But if you go another 360, 4 pi, everything goes back to the original shape. Okay, nobody believes this, right? So let's do this experiment. I need 4 volunteers. Nick, you're out there doing volunteer. I need 3 more people. I need this. And I need 1 more volunteer. So now, okay, so now the arrow is pointing towards you. Okay? So now give me some slack. So I'm going to rotate this this way, counterclockwise, 360 degrees. So let's go. Give me slack, give me slack. If you hold it too tight, the rubber will let go. So give me lots of slack, right? So we've done 360 degrees, right? I'm going to continue in the same direction. 180, 360, right? And now you think that this will never get undone, right? And maybe you're right.
You just need to turn it around.
No, this is all legit. I think. It's not working. I haven't done anything, right? I haven't changed anything. We're getting there. And now if you look, you find that none of the rubber bands are twisted even. Everything is back to the way it was. 4 pi. It's really fascinating. And somebody once said, oh yeah, but if you had more rubber band. And so I have 2 more up and down. It still works. So you can do this in C-dimension. That's it. So this is just an interesting thing.
And you can't untwist it with only 360 degree rotation?
rotation?
Absolutely not. But I'm happy to give it to you after the time. But it's interesting and a little mysterious. But that's how it is. Okay. Back to our original problem. So now we have to go back to this picture and talk about the point that Mikhail brought up, which is distinguishability. Distinguishability. So, you have insights?
I have an idea that it should be not just 4 pi, but sort of 2 pi in one direction, and then 2 pi in another direction.
But this was 4 pi certainly in one.
But then you used your hands.
No, I just moved the rubber. Right?
So
I didn't
that's
move
right.
the object.
Yeah,
only the
yeah,
rubber.
yeah. So, but I think if you did like 2 pi like this and then 2 pi like this, maybe the rubber would be okay itself.
All right. So the point now that we want to make is this business of indistinguishability. We are summing over states and we are overcounting the situation, because if I were to interchange 2 particles, obviously nothing would be different. We couldn't tell. Okay. So the particles are indistinguishable. We have to correct for this overcounting. And this was a problem. Originally, people who did statistical physics did what I did in the other room, and they ended up with something called the Gibbs paradox. And basically, the Gibbs paradox, the Gibbs paradox was the fact that the entropy of mixing didn't come out right. And the result is that we must correct if particles are indistinguishable. And basically, we just need to divide the number of states by this overcounting factor. And so, in the free energy, we have minus kT ln Q, and it is Q that we have to correct, and we have to divide by 1 over n factorial, the sum of e to the minus beta ei. Because here we are summing over states, but we are overcounting by n factorial, because we can make n factorial interchanges of the particles without you noticing anything. Now, if you have 2 kinds of molecules, so suppose you have a mixture of helium and hydrogen in an ideal gas, then you would have to have 1 over n1 factorial times 1 over n2 factorial, where n1 and n2 are the numbers of hydrogen and helium particles. So it's not always the total number of particles, it is the number of identical particles. That's what you have to put in there. Okay, and so to a good approximation, n factorial is n to the n. Stirling's approximation. And so we had things raised to the power n before, so we can just have n in the denominator. Take out the factorial from here as well, and then we recover what we had before. So the previous result for the ideal gas is is minus nkt, and everything is the same as before, except we have a 1 over n inside. So we had a v over n now inside, times whatever we had before, which was 2 pi k t m over h squared to the 3 times. Right, so this n comes about because of this correction. Okay? Everybody happy with this? And now,
There's an E.
there's an e. Well, you're right. I'm cheating again. You're right. The ln of n factorial is n ln n minus n. And that we can write as n ln e. Right? Ln e is just 1. So, so this should really be n factored out ln n over e. Right? And so there should be an n over e, so there should be an e here. But in fact, it turns out to be pretty small, so, but you're absolutely right. To this level of Stirling's approximation needs to be. Okay, and so that's pretty much the story. So, but the really important thing is that the Helmholtz free energy is minus kT ln q. But that's one thing you must remember if you forget everything else about this course. Free energy is minus kT ln q. And q you should be able to evaluate by this procedure we had. Just integrate over phase space, over all the q's and p's, Hamiltonian the Boltzmann factor, divide by the right number of h's, and correct for overcounting by having this factorial. And then you can derive the free energy for almost anything. What I want to do next is to have an ideal gas of rods, because the crystal molecule is kind of wrong, and put these in an electric field, and then we'll have some idea as to what happens there. Now, the difficulty comes when you have interacting particles, and it's difficult because each particle interacts with every other particle, and that makes life really complicated. And there are nice simplifying methods of dealing with that, called field theory, and that's mainly what we'll be using. But the essential thing is just this. The essential business is just to be able to evaluate the free energy. You can then get everything else from the free energy. How do you get the average energy from the free energy?
X potential value. X potential value.
Yeah, but how do we get it from the free energy? There's a really nice way to do it, which is just to know that if you take the partial of the free energy with respect to beta, it brings down the E. Right? And then okay, so the free energy is just minus kT, I'll write it as 1 over beta times ln of sum of e to the minus beta ei. And I'm going to take that other factor over here, right? Minus 1 over beta ln take the partial of f with respect to beta. No. Yeah. If I multiply through by beta to get rid of the betas over here, then if I take the derivative of that quantity with respect to beta, I only have this term, and if I take the with respect to the logarithm, I get 1 over this sum, and up on the top, I will get the sum with the EI. So if you multiply this guy through by beta, and then I take its derivative, its partial with respect to beta, so this guy's gone, this guy's gone, so we get nothing from here, so we just have this term left here. The derivative of that, first of all, gives us sigma e to the minus beta ei in the denominator. And on top, we'll have sigma of ei times e to the minus beta ei, except we'll have a minus sign here. Oh, but I have a minus sign here, so that's fine like that. And then you recognize this just as pi. So this is just pi, which is exactly what you want. So to get the average energy, you just take the derivative of beta f with respect to beta. And you can literally get everything you want from your free energy. So if we do this, here's our free energy. So if I multiply through by beta, this guy is going to be gone. So I have minus n ln, and beta only appears in here, right? All the other terms in this logarithm I don't have to worry about. So I can write this as the log of kt, which is 1 over beta to the 3/2. That's this term here. And then I have, of course, minus n times the natural logarithm of everything else, which I don't care about because it doesn't depend on beta. 2 pi n over 8 squared. So if I take the derivative of this with respect to beta, okay, nothing from here, so only this thing that matters. And I have a 3/2, which comes out. The minus sign goes in, so this just ends up being 3/2 n log of beta, whose derivative is 1 over beta. And that's 3/2 n kt, which is what we expect. You have half kt energy associated with motion along the x and y direction for each part. So this is what the standard is. Okay? So, but again, the essential thing is F equals minus kt log q over n factorial. Well, it depends on how you define Q, but it should be the number of states, the number of distinguishable states, and then Q we can calculate by integrating over P's and Q's and putting the Hamiltonian up in the Boltzmann factor. Okay? And so this is just a simple example for an ideal gas. And what I want to do next time is then take a gas of rods and see what they do, and even put them in an electric field and see what happens. And then the next things will turn on the interaction between the rods, and we'll have the magic system. Okay, so I'll stop here and hand the floor over to you, Ed, who will hand back your assignments. Okay.
We have a class on Wednesday and Friday.
Oh, that's a good point. We will not have a class either on Wednesday or Friday, because there's a liquid crystal elastomer conference going on, so no class. But we are somewhat ahead because we